All right, so today is one of the important lectures that is, on one hand, is going to help you understand what we are doing in Project 2. Right, so you can finish Project 2 before today, but it's really just to follow instructions. Today we are actually going to tell you why we are doing what we were describing in Project 2. So that is basically how do we properly reconstruct the flux for finite volume schemes. Right, so also if we have time, we'll also start finite element, which is really one of the most counterintuitive methods for discretizing PDEs. And today we are going to basically be laying the foundation of finite elements. Okay, so first of all, let's talk about finite volume. So in Monday's lecture, we looked at, we used two different schemes to reconstruct the flux. One is using the average of the cell averages for computing the flux, right? So we first compute the flux evaluated at the cell averages, and then we compute the average of the fluxes. So that worked pretty well, and in continuous and smooth regions. And near discontinuities, it worked better than if you are taking the average of the values, then compute the flux. But it still had some oscillations. Then we looked at an upwinding scheme. The upwinding scheme actually worked all the way to the discontinuity, but had some dissipation, had some numerical dissipations in smooth regions. And then we said that in a real finite volume code, we need to detect if we are near a discontinuity or not, and switch between a second order or even higher order scheme, like the cell averages, versus an upwinding scheme, which is first order but resolves shockwaves very well. Okay. But then we also had a dilemma that using an upwinding scheme, we were not really able to detect if a shockwave is fake or not. So we discussed two different conditions. One condition is that if I have my W as a function of X, and I have a shockwave that goes between 1 and -1. So we are solving the equation that is Burger's equation, plus W times dW dx equal to 0, which if you want to write in the conservative form is d dx of W squared over 2 equal to 0. All right, so the first scenario is a real shockwave. The wave on the left is moving towards the right, and the wave on the right is moving towards the left. So they actually collide each other and forms a shockwave. The second case is what made us concerned about the upwinding scheme is a reverse shockwave. So if we have an inverted shockwave while the solution is 1 on the right and -1 on the left. So the wave on the right is moving towards the right and the wave on the left is moving towards the left. And we found the two solutions that both satisfies the differential equation with no problem. I mean, both satisfies the integral form of the differential equation, right? With no problem. And let's first write down the integral form of the differential equation. The derivative of the total conserved quantity within any interval, plus W squared over 2, which is the flux, the difference between B and A has to be equal to 0. So this equation is satisfied by two different solutions. One solution is my W of X and T stays like that forever. It's equal to 1 or -1 if X is greater than 0 or X is less than 0. So that we can just easily see we are going to be satisfying the solution, because if the solution stays like this, the flux would stay as a constant, being half, right? No matter where X is, W squared is always 1, because no matter if W is 1 or -1, square of it is equal to 1. So the flux is always equal to half, no matter where it is. And the difference between two positions is always 0, okay? And on the left-hand side, if the solution stays the same, the time derivative of any integral is also equal to 0. So it's satisfied automatically. But there is also another solution. Another solution that not only satisfies the integral form of the differential equation, it even satisfies the differential form of the equation. It's equal to 1 or minus 1, but also it's actually equal to x over t. If x is greater than t, x is less than minus t, and x is in between minus t and t, right? So let's actually put a less or equal here. So in this one, you can even plug into the differential form of the equation and find out it's satisfied. So for example, when x is greater than t and x is less than t, the satisfaction of the differential form is automatic because dw dt would be equal to 0, dw dx would also be equal to 0. So the only concern is in this region, right? So in this region, let's say dw dt would be equal to d dt of x over t, right? Which is minus x over t squared. Agree? Okay. dw dx would be d dx of x over t, which is 1 over t. All right. So w times dw dx is equal to w times this, and w is actually x over t, so it's x over t. If you add them together, right, it's equal to 0. So the equation is satisfied. So that means we have two competing solutions, both. Oh, and we also said if something satisfies the differential form, then it automatically would satisfy the integral form, but not the other way for discontinuous solutions. Right, so basically we have two solutions. The blue and green solution both satisfies the integral form of the differential equation, but they behave differently. If you look at the diagram in space and time, x and t, the first solution, let's denote as blue, has a discontinuity that stays constant in space. And we have minus 1 here, plus 1 here. The second solution is smooth. I mean, it's not smooth, but at least the continuous, right? So in the beginning of time, it is discontinuous, but the discontinuity disappears after infinitesimal amount of time. Instead, I have a slope of 1 over t, which means the slope gets more and more gentle as time increases. If you draw the space and time diagram, these are the two lines of x equal to t and x equal to minus t, right? Of course, I didn't do the aspect ratio properly. But in this region, if I draw the contour, in this region, the contour of the solution is going to be like this. It's just like a fan. Okay? And this would be, on this line, I have w equal to 0. On this line, I have w equal to 1. On this line, I have w equal to minus 1. And w equal to half, something like that. All right? So basically, these two competing solutions both satisfies the integral form. And which one is correct? Green or blue? Continuous or discontinuous? The continuous solution actually is correct, because last time we said in a real physical system, I would have a infinitesimal amount, let's say epsilon, times a second order derivative. And that infinitesimal diffusion term would actually make this discontinuity a very, very sharp but continuous slope after infinitesimal amount of time. And when that happens, the first solution can no longer maintain anymore, and it's the second solution that would appear in reality. Right? Any questions?